Okay, hi everyone. Good to see lively already in the morning. Any quick reactions on trying to deal with the exercise? I see like this. Yeah, actually, I saw some smiling faces from talking with people about it, so that's good. I hope you find that, doing like a hands-on, trying to creatively think about numbers is useful. And if you have any other comments, less happy, come to us in the break or write us an email or something like that. We're really open. We want to make it the time you spend in this is a time well spent. Okay, good. So the challenge or the thing for today is making sense of big numbers. So what is making sense and what are the big numbers will become clear as we go along. Let's start with, anybody has a favorite big number? Google. Google is a very useful and favorite. Anybody remembers how much that is?
10 to the 10?
I think more. No. Okay, so already we have an example of how big numbers are confusing. Okay, so a really common big number is a billion, right? And anybody has let's just, I want to drill down for a second about billions. Anything that you remember hearing recently or that you know in general that are in the billions?
People on the earth.
So we have people. Something else?
Stock market.
Wealth.
Something, all sorts of things related to money. So yeah, wealth, stock markets, this, that, whatever. Anything else in the billions?
Age of the universe.
Years.
Speed of the light. Close to.
Speed sometimes. Stars. Good. Okay, so there's lots of examples. I would say the most common one that I hear is in respect to money. I'm guessing if I open any random newspaper in the finance section, I'll see it a lot, but also in other things, we get that a lot. And I think there's something a bit that could sometimes surprise because we see it relatively commonly. We sort of think we understand it, which might be true, but I want to put a small question mark here. And in order to check how much we really understand that, I want to ask you to do with me the following exercise. It's a tough exercise. You have to go to the equator, okay, to stand on the equator. And then you have to put a small ball we could do ping pong or golf. What is more popular?
Golf.
What? Golf. Okay, so we have some people who like golf. So you put a green, because we're talking about sustainability, it will be green. So let's put a green golf ball. And then you go and you're starting to walk across the equator. Okay, and you're putting regular golf balls, one after the other, one next to the other. Now they're white, like regular ones, and you put 1 billion such golf balls, and then you put another green one. And then you put another billion, and then you put another green one, 1 billion, another green one, until you do the whole circumference of the Earth, and you go back to where you started. Okay? I can try and draw it, but we saw from last time when I'm drawing things, it doesn't make them any clearer. But it's something like this, and we have this, and you started here, and you put lots of balls, and then you put a green one, etc. Okay? Now the question is, how many green balls would you put all together until you go back to where you started? Okay? It's kind of like, remember the Jesus Trail from last time? So the Jesus Trail, you could walk on water, no problem, so you can do it here. But now, Jesus is also busy putting those balls. Okay, the question is clear? Good, I think it's pretty well defined, so I suggest that you try and solve it. Okay, so there's a question before that?
Yes, what is the space between each ball that you put?
No space, you make them touch each other.
Oh.
Okay, so now let's take 5 minutes. Try to work in pairs, but if you don't like working with people, you can do it by yourself. and try to give me a number at the end. Okay? Let's do it. איך הולך? יש תוצאה או שעובדים? מה יצא? כמה? יצא לך? מה? עובדת על זה או שעוד עובדת על זה? 100%, מצוין. יש לכם תוצאה או שזה? אוקיי. Working on it or you have a result?
No, I don't know why it's so lustrous.
Okay, take your time.
זה אמור להיות, כאילו, אנחנו מחפשים יש קאץ', או שזה פשוט לחלק בכמות המערכות של הכדור.
כן, מה יצא לכם?
800 מיליארד.
אוקיי. אוקיי. איך הולך? יש תוצאה? מה? How are things? You have a result or you're working on it?
נכון, כן, אתה
כן.
מסיים כאילו. לא חשוב, כן, אחרי זה אולי לראות
To round. Okay. So first of all, thanks for engaging in this. It seems like you really looked into it. And I did a classic mistake that like I didn't ask you before, what's your intuition or what do you think is the result, something like that, because now obviously whatever I'll do, you say, obvious, of course, this is the result. So nothing surprises you, and then you don't learn as much because you didn't have a horse in the race, like you didn't bet on anything. But I would say, at least for me, and you know, a few years before that I was asking the question, we think usually about the world as very big, and as golf balls is very small, and therefore there's a space for a lot of them, right? Even a lot of billions, because we have billions all over the place. So now let's try to put that into what's relevant here. So we need to know, like, we could break the problem into something relatively simple. We need to know the length of the whole trail, and we need to divide it by the size of the ball, right? Good. So what's the overall length of going throughout the Earth? Okay, so so people know the 4, that's good. But now the question is,
4 times 10 to the 7 meters.
4 times 10 to the 7 meters, that's probably right, but for me it's hard. Whenever we do 10 to the 7, I prefer to work in units that I can immediately know if I'm right or wrong. So for this thing, I would start with kilometers, because that's more intuitive. Okay, so here's the thing, it's easy to be confused 4,000 or 40,000. Okay, so like, yeah, okay, or just empirically we see that happening. So the answer is 40,000, and either you know it by heart or you remember something like the radius, something. Okay, so this is 40,000 kilometers. By the way, maybe quick, so last week I couldn't come because I was giving a talk in Paris. And in Paris, a friend of mine said, there's hundreds of museums to go to in Paris, but say, on Sunday, let's go. I live in Paris, so I never go to museums. So now you come, you give me a good excuse. We'll go to the museum. They have a museum of science and matter. Art and matter. Art and matter, I said, okay, that's what he suggests, we'll go there. And believe it or not, when I go there, sort of like almost the first place we start is the place where they show, you remember from the lesson week before, I was telling you about how they defined the meter in the French Revolution. So it turns out the original meter that they defined was there in the exhibit. I have photos to prove that. So this was like really, I couldn't believe the coincidence of seeing this in front of us. I see people starting to become cold. Okay.
No, it was very hot before, so maybe.
So we'll do something in between, but I'm the. Okay. So what about our golf ball? Okay, maybe it's 5, but I like 4 just because it would work nice. So give yourself I think it's fine to give yourself some flexibility because we don't care whether the number is going to be this or 20% more. We're looking for the order of magnitude. So then you can do some convenience rounding of corners in terms of like the exact value. So we'll take 4, which actually I think is maybe even correct, or maybe I think the standard ping pong ball is 4 centimeter. Okay, so that's 4 centimeter, right? Good. So now the only thing that's left is, in this case, it's really simple. It's just to do some unit conversion. Okay, so this is 4 times 10 to the 4 kilometer. And in order to be really very clean about it so I don't make any mistakes, I remember that when I want to convert, I want to go from kilometers. I want to multiply by 1. I want to have 1 kilometer here. And let's move. I'll start with meters, so that's 10 to the 3 meters. Okay, and then kilometer would cancel with kilometers. Now I have it in meters. But I want to go to centimeters. Okay, not a big deal. 10 to the 2 centimeters is 1 meter. Divided by 4 centimeters. I know for some of you this is like so trivial that you say, what is he spending time on? But often when you start going to other things, you get messed up and then you're wrong by a factor of 1,000,000. So it's worth being safe than sorry in this case. So I have the 4 times 10, the kilometer with the kilometer, meter with the meter. I'll have centimeters, so good. 4, 7, 9, 10 to the 9, divided by 4, which gives me, this is centimeter and centimeter, which is nice. I get an absolute number of 10 to the 9. What is 10 to the 9?
1 billion.
1 billion. So nice. Okay, so what does that mean? 1. No, so now we could ask ourselves whether you'll still be able to put one more ball or not, or like it's on the verge. So I would say you'll never put another ball. Like, okay.
This is why we thought we were wrong.
That's why you thought. Okay, so there's all sorts of things that happen. I was moving around, so I had people that got a value of 1 and they thought they were wrong. There were people who thought they were 1 and said, this is so trivial. There were people who got 1,000, 1,000,000, 10. We had quite a diversity of results here, which is interesting, which I guess also shows, like, I think it's a good point to reflect, like, again, we all have this imposter syndrome that we think all the others are really smart and just we're not smart. But then just let's, a reflection of the situation here, except for those who thought it was really easy and they did it correctly and they got the right result and they knew it all the way long. All the others, there was quite a diversity here, even on this thing that is, again, this is not rocket science. This is like, dividing two numbers, which are in units of size. Okay, so I think it's just a good thing to reflect on the fact that, again, when you start to play with numbers and big numbers and something that's new to you, you can get confused. And that's why it's good that we have this course and you'll get better at it and just in general. Okay, good. So this was just about 1 billion. And I take from this, except for being able to do nice calculation, is that it now tells me, for example, I don't know about you, but I'm trying to change things in the world. Like, for example, we have, these big problems in climate, sustainability, food, other things. And so I'm saying, we need to change things. And then, we're doing through our science, through other things. And you hope that this would make changes in the world. But then, actually, very often you get discouraged or like you really become depressed because you say, nothing that I'm doing is really making an impact. I was saying this for a long time and still things did not change. Humanity did not change, whatever, what it eats or, how much, how cold the air conditioning is or all sorts of other things. But I think for me, with this analogy, that like thinking, okay, the humanity is like, all these ping pong balls across, the earth. I'm like a small one ping pong ball. And now you think that, let's say, you're on the equator and you now, as a ping pong ball, you decide, okay, I'm going towards the pole. You start to going, and now you expect humanity to follow. now like it's so many people, and it's 8 billion. Okay, so it's 8 times around the Earth of ping pong balls or golf balls, and you expect them to. So it's not so easy. So that I think shows something also like the immensity of humanity, the immensity of changes in humanity, and then what can you expect? Usually, like if you move maybe a few balls around you, would also move. This is kind of like work in your sphere of influence, but it's tough to expect everything to change. Although that also sometimes happens, and science is actually a good way for things to propagate because it's true, so it shows itself. But it just anyway, that was a bit more philosophical than I ever do in the course. So let's stop here. Good. So now that we dealt with this, I want to move a bit further in terms of our intuition for big numbers. And for that, I want to go back to something that I heard somebody telling me. I just think how. So a few years back, there was like a big outcry in Europe because they found that some of the beef that was sold in supermarkets, for as like regular beef, is actually coming from horse meat. Anybody heard about that? Yeah. Okay, and that was like, it was a big, big thing. Okay, now when discussing that, there was an interesting professor that wrote a piece in the Times in England, in London, where he was asking the important thing is not whether you find a piece of that there is some fraction of that, because how can you find out? Well, let's talk about how do you know? Everything looks kind of the same. Maybe you have a very, very good taste buds that you can tell between this and that. But let's say usually there's you need a different scientific method to do that.
DNA test.
Random samples. Okay, but DNA test. What do you do in the DNA test?
Antibodies.
What?
You can check for specific antibodies for certain.
Okay, antibodies. Alignment. Yeah, by alignment. Okay. Okay, you take a sample and then what? You sequence it? Okay, anybody has an easier way? I think we're very sophisticated. We have like just such good tools, yeah?
Genotyping. Like if you have different genes between cows and horses, you can use certain primers that fits the horse gene and doesn't fit the cow gene.
Okay. Same. Okay, so so you can PCR it, right? Like you can, yeah.
I was just thinking maybe it's like the bathtub of who was this guy who went to figure out if there's gold in the ground. Maybe you have to do something with the density.
The Eureka movement of
Maybe you
Archimedes.
can find the amount of protein or fat in the meat and the different.
Okay, so there could be something like that, but then this would be very tough. It would be kind of almost like the taste because there's a lot of variability in the fat content and whatever. But I think that you could do things just like you were saying here. You could just amplify it with really cool methods, and then you don't have to necessarily sequence everything. You could just check between this and that. Okay, so this gives you like a fantastic also resolution. You can say because our methods are so good that now even if you have like one piece of DNA from a horse and you specifically look for that one, and then you have this process where you amplify it a lot of time, and then you check, poof, you can find it. So he was making the case that, the question is not whether you have this or that. The question is, what are the implications of that? How much is that, affecting our health or the content or something like that? Okay, and he was giving, he was mentioning that, actually in every breath that we take, there's actually molecules from the last breath of Napoleon. And he said that, his teacher told him that, but he always thought it's an urban myth. But now the question is it an urban myth or not? So let's start with just your gut reactions.
It's a myth.
Okay, who's voting for a myth?
What was the unit? A molecule?
Molecules, yeah. Who's voting for not a myth? Good, so we have half and half. It could be like it's worthwhile checking out. Any suggestions of how we go about it? So try to think for yourself. I could make you do it again, but now I think we'll. Okay, I see there's a lively discussion. Anybody wants to vote to change the vote? Okay, so let's try to analyze it together. Okay, well, how would you approach the problem? So,
Start from the volume of our lungs.
okay, so there's a suggestion here to start with the volume of our lungs. Okay, good. It sounds reasonable. Like if I'm taking a breath, and the question is whether the last breath of Napoleon before, I don't know, they killed him, right? So, or like maybe he died at old age. Whether there is or not, that's a good place to start. So, what's the volume of a breath in the lungs?
Few meters.
4.5. I don't think every breath is that much. Few liters.
Okay, let's make it a liter just to get. So let's say 1 liter. Okay, because I'm just thinking, how much is this? This is like, half a liter or something. I think it would be. I think maybe maybe we could do a few liters, but I think it would be. I don't think I'm doing more than drinking all of this twice. This is a liter. I think it's difficult for me to think much more. Okay, I never thought about it. Maybe somebody afterwards checks what the average breath. Actually, okay. So Liad has a good suggestion. If I do for a balloon, every time it comes, I would say it increases, let's say, by this, and this is half a liter or so. Okay, good. 1 liter. Okay, we solved the problem. The first part. Okay, what's the thing on the other side?
How many molecules?
So now we need to know how many liters are in the atmosphere. Okay, how do we do how many liters are in the atmosphere?
We know that the pressure is 1 atmosphere.
You know what?
The pressure is 1 atmosphere, which is equivalent to 1,000 millibars.
Yeah, so the pressure is 1 atmosphere. Good.
Why did you take the surface of the Earth, multiply it by about the height of the atmosphere, and assume it's close enough?
Awesome. So the suggestion is let's take the surface area of the Earth, multiply it by the height of the atmosphere, and then we have the volume. Good. Let's do that. So we have 1 liter. We got it. Now we want to do the volume of the atmosphere. So we need the surface area. Anybody knows anything about the surface area?
5.1 times R. Did we? That was in our
We did it last time. It's true, and it's also nice. It's like all the kind. Like we remember the 5, but we stuck with the rest. Okay. So how do we go about it? We could do the calculation again with the 4 pi something. But when I was thinking, maybe let's just we don't need exactly the right number. We just talked about the Earth, a few minutes ago. And the one thing we remember about the Earth is that if we go, say, this is how much?
10,000.
From here to here, we know it's 10,000 kilometers. Okay, which means that now, let's say, if I want to take the surface, let's say I just, I peel it like an orange. I was peeling an orange this morning, so I have a good intuition for peeling oranges. So I could say if I take just this, let's say I was like, let's say I'm just opening it up. Okay, how much did we say? We just need the whole circumference, right? So if I'm taking this and I'm opening it up, it would be something, I don't know, shaped, some strange thing like that. But let's just make it simple. Let's say I just want to know, how much would that be when I'm cutting it and peeling it over? We said this distance is 40,000, right? Kilometers. And this is 10,000 kilometers. So far, so good? It's not exactly, you can't really peel it 3-dimensional and 2-dimensional, but let's say, so it's kind of like 20,000 kilometers times 40,000 kilometers. No! Why not? Yeah.
Eventually, we're going to multiply everything by Avogadro number. So all of those 4 2s, we can treat them as 1. It doesn't matter. If the argument we hinge on if it's 4 or 2 or 8 or 10.
I agree. That's why I don't care about the geometry when I try to peel it off exactly. And it's true I don't care exactly about the 2 or 4. But if I don't give you anything, people here would, So I'm doing like something in between. I know that this is true, but let's just, roughly to understand, and then we could round things up. Okay, so let's say if I do that, you could keep on thinking about it. So now I have 2 times 4 is 8. Let's make it 10. And then I have times another 10, 10 to the 3, another 10 there, and 10 to the 3. So 1, 2, 5, 6, 9. 10 to the 9 kilometers squared. Okay? What do you remember as the accurate value?
5 times 10 to the 8.
Okay.
So
So,
rounding up.
so within a factor of 2, this got us right. And we also understand even where the mistake was, right? Because when I was peeling the earth like an orange, you know, there's things missing in the corners. You know, there's sometimes this nice cartography that, you know, why they do the earth looks something like this or something. So this is like what happens when you actually try to take a two-dimensional, three-dimensional and smash it on 2 dimensions. And there's some empty spaces, and this is the factor of 2 mistake. Okay, but I don't care. 10 to the 9, that's like the order of magnitude. Okay, so we did the surface area. What about the height of the atmosphere?
10 kilometers. Roughly.
Okay, that's true. 10 kilometers. You can think about it in different ways. A, you can just remember it. Although, you know, there's no really well-defined height to the atmosphere. Actually, I think when in the definitions, it's like when they say when you reach space, anybody knows? When do you actually define as reaching space?
When the atmosphere ends.
Yeah, so where? So is it 10 kilometers?
400?
Yeah, so I think 100 kilometers is what is defined. When you're more than 100 kilometers, then you're out of the atmosphere. But then, you know, there's an exponential decrease in the density, and therefore you wouldn't say it's a height of 100 kilometers. So you can do the effective height. What is the effective height? It's like if you took the atmosphere, the density goes down. But if you say, if I fill the atmosphere in the same density as what I have on Earth, how high would then it be if it was, and then it's 10 kilometers. Okay? I hope it makes sense. Good. Another way, by the way, to remember it, just roughly, is that one at what? Everest. Yeah, so that's maybe a good. So what do you know about the Everest?
8.4.
What do you? How does the Everest helps you?
You know, it's the atmosphere there is thin enough for you to have a problem breathing. So
Okay, and the height?
about 8,000.
Okay, so it's about 8,000, meaning 8 kilometers, and the density now, the air is much more rarefied, and therefore this is a good scale. And 8 is 10, so 10 kilometers. That's another good way to do it. Another final way to do it is that I remember that when talking about atmospheres, you can convert the atmosphere, it's a bit more complicated, but atmosphere is like 10 meters of water in terms of pressure. Like the pressure of one atmosphere is like 10 meters of water. You know that when you go scuba diving and things like that. Okay, so 10 meters of water. And I know that the ratio between the density of water and the density of air is how much? So that's actually a good number to remember because it's easy and makes life, you know, you could do all sorts of inferences with it.
1,000.
So it comes to 1,000. Like, now you can reverse it and say it's 1,000. Okay, like water, say 1 meter cube would be a ton. Air, 1 meter cube would be 1 kilogram. It's a density factor of about 1,000, which means that if I have 10 meters of water, it's like 10,000 meters of air. And that's the height of the atmosphere. Okay. Good, we learn a lot. Okay. So now this was the, so I have now, I know that what I have here is 10 to the 9 kilometers squared. That's the area times 10 kilometers for the height. Okay, we want to go to liters, so let's go from the, so I need to get rid of the kilometers and I want to turn it into, let's start with meters. So every 1 kilometer would be 10 to the 3 meters. And I need to do everything 3 times because this is cubed. Okay, so I have 1 liter, and here I had 10 to the 9, 10 to the 10, 10 to the 10 kilometers cubed times 10 to the 9 meter cube per kilometer cube. Okay? So 1 liter, 10 to the 19 meter cube. And last thing, I want to go from meter cube to liter. So I'll get rid of 1 meter cubed. Right? This is what I want to get rid of. How many liters are in a meter cubed?
1,000.
1,000. Okay, so I'm getting 1 liter within 10 to the 22 liters. Okay, this is the atmosphere, this is this. So far, so good? Okay, we're almost there. Now we need to think about, okay, the other thing, we want to know about molecules, right? Okay, so how do we do that?
Ideal gas law.
Okay, what about it?
Yeah, the radiation.
Okay, so here's now is a bit of a tricky part because this is something, like in a way, I'm guessing most of you have learned it at some point. You've learned it many times or whatever. But then it's also, it's like moving. We have a challenge here. We need to go from the macroscopic world. Macroscopic world is where, us humans live and the earth and all that. We have to go into the microscopic world. The microscopic, when you want to start to talk about molecules, molecular biology, chemistry, physiology, blah, 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 you have to go usually physics. You have to go from the macroscopic to the microscopic and back. And there's a door, there's a quantitative door that takes you from here to there, and it's called Avogadro number. Yeah, that's the door that takes you from the microscopic, and we'll do it in yeah.
I just remember from physics class the experiment that calculates this constant. You have like a drop of oil that you put on this water bath, and you assume it's a one molecular level, so you calculate the volume of the cylinder that it will create, and by the density of the oil you can get to the number of molecules, and then, but I don't think it will take us fast to what we want.
Maybe we should do the experiment here. But so actually, there's a beautiful thing written by, what's his name? There was the ambassador of the United States, I guess, before the revolution, after to France. What is anybody here knows some history? What? Yeah, we could look at Hamilton. But is it Franklin? Was it Franklin? What? I don't think it's Jefferson. Jefferson was in Hamilton, but so maybe it's not. Maybe it's not. No, but who was a scientist that was a Franklin? Yeah, it was Franklin. So yes, so maybe it was a later. Anyway, I'm getting a problem here. It's all on YouTube. Anyway, so he has this beautiful thing that he wrote. That he did this experiment. He was next to a lake that he knew the area, and he saw the waves there. He took like a spoon, he took a spoon of oil, and he threw it in there, and it quieted the waves because it created this. That was his hypothesis, that he put like a monolayer. It dispersed on the lake. It created the monolayer that changes the surface tension. Surface tension changes the waves, and then it quiets the lake. From that, he could infer things like Avogadro number, because then you have, if you assume it's a monomolecular layer, you can do all sorts of cool stuff. Anyway, we're not going to do that right now. We'll just try to infer it from things that we already know in order to have this door open to us at any time that we need it. Okay, so what is the issue? We know the ratio between the last breath of Napoleon and the volume of the atmosphere. Now the question is how many molecules we have in every breath. Okay? Why would that help us? Because we sort of we're assuming that the last breath of Napoleon, he got out some molecules, they got mixed up, and now I'm taking some fraction of the atmosphere, and the question is, okay, how many molecules were emitted, and then what's the chance that now I'll have one molecule? Okay. So how do we do that? Avogadro number, right? Okay, so what's this thing with Avogadro? What is the challenge of going from the microscopic to the microscopic, yeah?
In 1 mole of air, you have 22.4 liters, right? And then in 1 mole, you have 6 point something to the 10 to the 23 or something like this. So we can go from volume to number of molecules.
Okay, so that's an excellent way to go about it. That's roughly like a good way to do it. Let's unpack it together, and maybe we'll simplify some things along the way, but just so that it would be easy for you. Okay, so the challenge of this Avogadro number is to go again for the macroscopic. So you want to say, if I have, say, a weight of something, how many molecules would I have there? Okay, and they did a nice thing like they did with the meter. of like having a definition that would be somehow elegant. Also in here, people, smart people thought about some elegant definition, and they said the following. If I have 1 gram of the simplest, lightest material, what would that be? In terms of, so the simplest structure is hydrogen, right? You have like 1 proton, and you're done. Maybe an electron, but it doesn't weigh anything. So 1 gram of hydrogen has Avogadro number of molecules. Okay, if I know that, then I have a weight, I have a number, and then I could do anything I want. Okay, let's play with it for a second, and we'll see how that is all useful. Okay, so now the question is how much is that? So lots of people found all sorts of cool ways. By the way, there's also like a nice table at some point of like, whether, now it's easy for us, you Google it, right? But at the time, it was, it's not easy to find a solution to that, and there were all sorts of nice tricky ways. So there's a nice table of how, with different methods in the 19th century, and they found like, 20 different approaches how to find the Avogadro number, and they were actually pretty close to each other. It's quite a piece of science history. But now, what is it?
6.023 to the power.
Yeah, so 6.023 to the power something. So this is, I just, let me enjoy for a second. It's again a case where usually people, almost everybody remembers the 6, and usually half of the people remember 10 to the what? Which is again interesting that like, obviously if you don't know what's the power, it doesn't matter so much if it's 6 or 6.023. Okay, so indeed this is about 6 point something times 10 to the 23.
So that's easy, that's 1, 2, 3.
1, 2, 3. Yeah, that's a good way to do it. So there's a good suggestion, 1, 2, 3, then you remember it's 10 to the 23, but I'm going to ruin it. Because I would say, I think about this 10 to the 24. Okay, just because, again, within a factor of 2, for most of the calculations I care about, it doesn't matter so much. Although maybe if you like to think not in a linear way, but in exponential way, it's just 1, 2, 4. So it's also as logical. Okay, so 1 gram of hydrogen is 10 to the 24 atoms. Okay, how does again, if you wake up in the middle of the night or you need to do a quick calculation, if you remember this, you can get there. Okay, how does that help us with what we need to do now?
Why the gram per liter is.
Okay, great. So we say we have 1 liter. Now we want to go from 1 liter. We want to convert it into number of molecules, right? That was our challenge. Okay, the problem is I don't see liters here. So what do we do? Yeah, so I need to go from liters to gram. So the question is, how much does a liter of air weigh? What?
You said it's 1,000 times less than water?
It's 1,000 times less than water. I did say that. Good point. So what does that mean? So how much does a liter weigh? 1 kilogram. So how much does a liter of air weigh? There you are. I told you it's going to be useful. I actually didn't plant it on purpose. It's just, it came out nice. Okay, so we have 1 gram now of air. Okay, so how many molecules? Okay, so I was waiting for somebody to tell me 10 to the 24 because, we just had this. 1 gram is 10 to the 24. But there's a small point I see like this. Okay, because this was for hydrogen. And now we're not with hydrogen. In what business are we at? Nitrogen. Okay, so what's the difference?
5.
Yeah, so instead of hydrogen, I have here an N. Actually, it's an N2. Not that we care so much, but still. And what's the weight of this? Yeah, so each N is 14. And together it's like, so that would be like 28 molecular weight. MW, molecular weight. That just says how many times more than hydrogen this is. Okay, so it's 28 times more. Okay, which means that 1 gram now of air would be how many molecules? So instead, so it was 10 to the 24 if it was hydrogen, but because this weighs more, there's less molecules, so I need to divide it by, by few tens, right? I write this, few for, one, like 3 or something like that, few tens. Okay, so I get here few times 10 to the 22. Okay, this is usually not how you do algebra, so just let's make sure that you're not confused about what I'm doing here. This is few times 10. 10 to the 24 divided by 10 is 10 to the 23. And then divided by few, it's few times 10 to the 22. Okay, I see some smiles, but it's because you don't understand it or because you do understand it?
Why is dividing by few also like dividing by 10? Doesn't few round down?
Yeah. So it's like there's this funny thing. So few, by definition, is few times few is 10.
Yeah.
Okay, so 10 divided by few is few, which means that if I have, say, 10 to the 24, I can write it as 10 to the 23 times few times few. Okay, and that's... Okay, you can afterwards look at it some more. Okay, so we had few times 10 to the 22 molecules in every breath. Okay? Which means that if the density of Napoleon's last breath within the atmosphere is 1 in 10 to the 22, that's how much of the atmosphere he polluted in his last breath, 1 in 10 to the 22. Now I'm taking up few times 10 to the 22 molecules. I would have few molecules from that last breath. Okay, let me see if there's another. Anybody wants to explain it differently, or there's a better way to think about it?
But what about the time between his last breath? If maybe I didn't understand the question, because it seems like we already breathed his air.
Yeah, so we breathe the same atmosphere that he was breathing. But let's say, I don't know, there were two in the beginning we had, now I can go back to when I asked it. So there were half that thought it's bullshit and half that thought it makes sense. And so the question was whether it's the specific molecules. If I was tracking all the molecules that were coming out of his breath, now the assumption is that they dispersed throughout the atmosphere. And we could talk about it, whether it's true or not. But now they dispersed there, and now I'm taking up 1 liter in this breath right now. So I'm taking this fraction of the atmosphere. And now, which means that I'm taking this amount of molecules. And within those molecules, because the fraction is 1 in 10 to 22 that are from his last breath, it means that if I took this number of molecules, on average, I took a few of those molecules that were in his lungs. Yeah.
Don't we need to also multiply the denominator by few to the 10 to the power of 22? Because we're saying our nominator is molecules and our denominator is liters.
Yeah.
We're saying like a few molecules per liter?
Yeah.
What do you mean?
So the short answer is no.
Okay.
But I don't have a good way now to explain it very intuitively beyond what I just did. So I suggest you think about it. Like I'm not saying it's actually a good way to. I was also feeling a bit uneasy about whether it's clear enough, so keep on thinking about it. And if I'm wrong, I'll be happy to find out that I'm not breathing this air.
So,
Yeah.
something is missing to me from this calculation, which is, let's say that Napoleon was not a usual person, but extremely big one, and he had 10 liters, or that I'm a very small person and I take very small breath, so those two numbers should somehow enter here, and I don't see it. Everything cancelled out perfectly, and I don't see it.
Yeah. So I hear you. I think it's kind of like the question before to some extent, and also I can't right now give you an answer that would enable your intuition to find. Let it think, and you'll see why it does cancel, how it works out. But now that I took a second to sip some water, and I'm a bit worried that maybe in drinking this, maybe I'm also drinking, you know, from the last time that I know Napoleon had a peace or something. So what do you think? We make a vote again? So who thinks that, you know, in the sip of water that I took, there's some molecules from the last time that Napoleon went to the restroom before he had to die? And who thinks that there's no chance?
It's not the same numbers, it will be the same answer.
Like water circulate much less than air, so you cannot assume like the pee of Napoleon circulates all the way around. It's much more like steps of assumption to do in this case.
You have more oil than
Okay, good. So let me just wrap up what we had here. We had a lot of. So A, you said like, you know, it's all the same. You know, water, so it would be the same thing. Other people said, you know, there's much more water or much more air. And what was the other? There was like.
About circulation.
And there's the issue of circulation. Okay, so I would say it seems like an interesting question by itself. So you want to calculate it? So let's try to see if we could calculate it without. So what would be the relevant things to? Should we do it now? What do you think? We don't have much time. Okay, I let you think about it. I let you think about it. Actually, it's very much in the same spirit. And yeah, you have a question, comment?
No, I just wondered, just thought, if we have to take into consideration if it matters the evaporation of what happens, or if it's just all coming back in the end.
Yeah, so we're assuming the hydrological cycle is that, you know, water stays water. So, you know, it goes up, comes down.
And eventually it will be in the ocean again.
Yeah, so it's still, unless they, you know, put it into the museum in Paris the last time he went to the, you know, because it's Napoleon. Otherwise, I think it went into the hydrological cycle, so it's somewhere out there. Although you could think about, say, the mixing time. So the mixing time in the atmosphere is about 10 years. The mixing time, I think he died in some small island. He was like, you know, deported in some small island in the Atlantic. So the mixing time in the Atlantic with the, I don't know, the aquifer of, we're doing desalination of water for the Mediterranean. So the question is, how fast, how is the mixing between the South Atlantic and the Mediterranean? A short answer is I don't know exactly, but it might be, maybe it doesn't mix so well. But let's, for the fun of it, let's say it did mix. I would say you can, so, but just to see your intuition, who think this is, there's no chance that I just got something from Napoleon in my water? About half who's voting that, you know, there definitely is.
If you avoid the mixing, so.
Okay, also, so it seems like people are raising their hand much, much lower now. I don't know, something is happening here, we're not doing very well, or you become really tired.
Do we
So
assume that water stays water?
you have other suggestions?
Photosynthesis?
Okay, that's a, okay, so that's a really cool thing. You could say, okay, maybe now within that time scale, the water is not water anymore because within photosynthesis it turned into, I don't know, a forest. What do you think?
There's a lot of these algae in the ocean. There's a lot of things going on, I think. But I don't know, percentage, I don't know. Can you neglect?
I think all of these processes going inside the mixing. Like,
So I don't remember in the exercise for this week, did we have something about all the forests? Or didn't put it in the end? Okay, so you guys are supposed to know the answer. Like to be able to say something intelligent about this. Anybody sees a connection between what you had in the exercise and this question?
and the ratio between.
Yeah?
So a fraction, like the ocean is sort of as deep as the Everest, and we know the surface of the Earth, and a large fraction of it is water. So we sort of know the volume of water on Earth. So we can do a calculation and then compare it to all the trees on Earth, and see that obviously there's much more water than trees because otherwise there wouldn't be life on Earth. There has to be a huge reservoir of water for this to
Okay, so something along those lines. I don't remember if did we have this thing if you took all, yeah? Biomass, something with biomass. Okay, what about biomass?
No, because
It's really thin layer, and the water is huge layer.
Okay, so look at this something. Okay, so look at this. There was an interesting logical progression here. Okay, somebody was asking, okay, what if the water now, went into photosynthesis and therefore it's not out there in the ocean yet, right? The same molecules. Okay, which I think is a very fair question. Also shows like thinking big picture about the whole thing. Okay, but now I want to do a quantitative estimate. Otherwise, we're left in this discussions. People, I think it's a big problem. Somebody else thinks it's a. We have to find a way to. So actually, you have the answer from the. We didn't plan it really. Like it's like you calculated in the exercise. If you take all the living things on Earth or all the plants, which is effectively like all the living things, and you put it into a layer, how much would be the width? How much did you get? Something. Yeah, so we don't remember exactly. I hope you remember. I didn't check the exercises yet. But it's something like, a millimeter or something like that, right? Okay. So now, how many years ago did Napoleon die?
1851 or 1821.
Okay, so 100. So if I have, so if the width is 10 millimeters, over 100 years, let's say I'm taking everything for all of it, the width of it is going to be how much? 10 millimeters every year, 100 years. It will be 1 meter. Okay, maybe it's a few hundred years, few meters, whatever. In terms of the ocean, the water in the ocean, tiny fraction. Okay? So now you see, again, there was a nice logical thing to say, maybe this, and then very easily, with something else that you know or something that you play, you can show nobody cares. It's negligible, negligible, negligible by orders of magnitude.
like drop in the ocean.
Drop in the ocean. That's what I was looking for. This is not working properly. So indeed, drop in the ocean. And I think this also shows you like a bigger point, and that is like, once you're in the game, it really is like a superpower. Like you can really do all sorts of cool inferences and things connect in all sorts of ways, and you can see things. Okay? Good. So before the break, I want to mention something, and then you can go and explore and do something, and that is, so just about the thing with the water, you can, if you want for fun, you can calculate it and see what comes out. But I want to talk about something called ocean bottom trolling. Anybody know something about that?
What's the final word?
What?
The final
Trolling. Trolling.
Oh.
Yeah.
Taking a big net and you're putting it across the floor, you're picking up everything, and even if it should live there, it's being picked up and it's being killed.
Yeah. Okay. So yeah.
I don't know how to explain, but I just thought that every time they take something from the bottom of the ocean, there's like a few hundred species that they never seen before, something like that.
Yeah, and those species is basically aliens, isn't it?
Okay. So it's a common practice of it's one method in which seafood arrives to our tables, and that is indeed of doing going to the bottom of the ocean and trolling. And the question that we want to analyze after the break is how many meters square of the ocean bottom has to be destroyed for every shrimp that you get from there. And so in order for you to, we'll see how we could try and analyze such a crazy question. But for that, in order for you to know, again, those who do not know what is it all about, etc., you'll find in your inbox, right, like a short video from David Attenborough documentary on the ocean that shows how does that work. It's not the happiest video clip you ever saw, so take it, sit down, or it's a sad practice. But it would give you the relevant know-how to be able to discuss it further. Okay, so we'll take now a 10 minutes break. Everything is 10 here, so we'll take a 10 minutes break and we reconvene. Okay, so before, I know some of the people got the video, some people did not get the video. You can watch it, when you see that you got it. Before we drill down into the shrimp, I want to go with it. So what is the logic that we're trying to follow? We're trying to make sense today of big numbers. So I hope that I established before how our intuition is not that amazing necessarily for big numbers. On some big numbers, we understand it really well. On some big numbers, we have to improve, and we have all sorts of good tricks in order to be able to handle it. And now I want to take this statement that I heard. There was a paper pretty recently, it got quite some headlines, talking about the number of ants in the world. Okay? They were estimating how many ants there are all, in total. And they were giving the following 20 quadrillion ants in the world. Which is the sort of thing not unlike all sorts of things that you might see when you listen to a lecture. They're giving you some really impressive number. And I think it's very helpful if you can do a sanity check. If you can find whether it's, to be able to say if it's true or not, and what does it, to try and put it in some context. Okay, otherwise, you're left with this and you don't know what to do with it. Maybe you don't even know what to do with it because you don't even know what quadrillion means. Right? Okay, so maybe we should start with that. 10 to the what is quadrillion? And what?
I said 12, but what would be 4, so it doesn't really... is it 4?
Okay, so it's actually good to have some classic training in something that you know what quad means. Quad sounds like what? 4. Okay, so actually I didn't know that before I started teaching the course, but somebody taught me that, you can think about it as like million, and then you have billion. This I did know before, and then you have trillion, right?
And then you have quadrillion.
Yeah, so you can see there's actually a logic here. Mil is B is 2, 3 is 3, right? And quad is the next one. Okay? That's why it's quadrillion. Okay, it seems like you're already happy that you took the course, right? What would be the next one?
Quintillion.
Exactly, quintillion, which is like 5. Okay, etc. But that you don't meet so much. Okay, so how many is 20 quadrillion? So this would be 10 to the 6. This is 10 to the 9. This is 10 to the 12. This is 10 to the 15. Okay. Okay, so now you know what it means. They're saying there's 2 times 10 to the 16 ants in the world. Okay, now the question is, did they get it right or not? What do you think? Yes. Or no? Okay, so we left with, then you have nothing to do because maybe you met some ants in your life, but you don't have that strong an intuition. So the question is, how can you still check it? So how would you do a sanity check? Yeah?
Break down what it means per square meter, how many ants there are in 1 square meter.
Okay, so what's often very useful is to try to convert it into units and things that you know, right? Square meters we know, and we've seen some ants, and we've seen places where there aren't any ants. So this could take us a long way because we don't know about the whole globe, 20 quadrillion or not. Okay, so that means that if I take this and I divide by the number of square meters, I get the density. And again, these densities could be much more, we have much better intuition. So what do I need to divide it by?
The land space or surface area.
Yeah, so I need to divide by, the land area, maybe globally. Okay, how much is that? Yeah, so one third of what we calculated before, right? And so we did it so many times, I won't do it again. But the accurate thing was like, about 500 million square kilometers, which was like 5 times 10 to the 14 meters squared. Okay? And now I need to do 1/3 of this. So I get 2 times 10 to the 16 ants divided by 5 times 1/3, I'll make it a 2. Again, the convenience that I have, 10 to the 4 meters squared. 14, which gives me 6, 2 and 2, 10, so yeah, 10 to the 2 ants per meter square. Okay, so I didn't do anything, like it's the same thing. It's just like the paper, instead of saying there's 20 quadrillion, and then, or the heading in the media, you said there's about 100 ants per square meter of land in the world.
How many square meters is this graph for?
So this would be about 10, and this would be about 10, so it would be 100 square meter. Okay, yeah?
Could one other method be to try and see the fraction of ants compared to all insects?
Yeah, so there could be all sorts of other sophisticated things. Now, because we're also short on time, I won't get into all the smart things we could say about this. I just want to finish with the fact that like this is a way, now I feel like on much better ground. So first of all, is it bullshit or not bullshit, which is like the original thing. You want to do a sanity check? I would say, if I look here, I don't see 100 ants. But then in a place where there are ants, I don't see 100. Usually they have like a nest and you have like 1,000 or 10,000 or whatever. So in general, I would say 10, and I know ants are ubiquitous around the earth. So I would say this generally passes the sanity check. Okay, I have much more intuition. Like if they were giving me, like millions of ants per square meter, I would say no, it doesn't sound right. If I tell me there's, 0.00, but this, now that I moved into this, I have a much, much better intuition. Okay, so doing some sort of normalization or putting it in that context is a way to make sense of big numbers. Okay, so that's what I wanted to do. In the same spirit, I'm going back to the question about the bottom trolling. So let me give you some values about that. So, okay, so we go with boats, and every year we do this trolling. We go through the surface of the ocean with big nets. And now what we know, what do we get out of it? So the weight of everything that is being collected, you can Google it or ChatGPT it or something like that. Roughly what we could find is that that's about 5 million tons per year. Okay? That's the weight of everything that you collect in this. 5 million. No, what? 5 megatons. No, this is everything. Now I'll talk about everything. Yeah, everything. So shrimp as well as other things, etc. Just a second. Yeah. Okay. And now, what's the area in which we're doing the trolling? So interestingly, it's the estimates that there are of the area that is being trolled is also about 5 million square kilometers per year, which is roughly the area of what? Anybody cares any area in their head?
What's the number?
5 million square kilometers. Yeah, so how much is the area of the USA? So the area of the USA is about 10 million square kilometers, which is also the area of China, which is the area of Australia. Okay, so this is like, we're talking about like continental, small continent style that you troll of the ocean, and you get this. Okay, what can I infer from this? So this would be about 5 times 10 to the 6. Let's say instead of ton, let's go to grams. Okay, this is tons per year. I can multiply, I want to go to 1 ton, that's 10 to the 6 grams. So this gives me 5 times 10 to the 12 grams per year. And similarly here, I don't want to work in kilometers. I can just convert it into 5 times 10 to the 6 kilometers square per year. I can go to meter square, which is what also the unit we were interested in. So 1 kilometer is 10 to the 3 meter, and then this is squared. So it's again 10 to the 6, and I'm getting 5 10 to the 12 meter square per year. Which when I divide the two, 5 10 to the 12, 5 10 to the 12, I get 1, and the unit is
Grams per meter square.
grams per meter square. So from that I get 1 gram per meter squared. So this type of, of production or something, or hunting or whatever you call it, you're getting about an output of about 1 gram of something you can take per meter squared. And now you can think about, say, a shrimp. How much is the weight of a shrimp?
Would you not try and think of it as in the percentage of shrimp in a catch?
Again, you can do it a different way, but let's do my way. So the shrimp, they could vary by, the small shrimp, big shrimp, etc. I would say, if I take a shrimp cocktail, it's like 100 grams, and there's like, say, 10 shrimp there. So every shrimp, normal size, average size, about 10 grams. Okay, so for the shrimp cocktail, it's the size of this classroom. For 1 shrimp, it's the size of your, room. That's roughly the number, although I would say many of the shrimp we eat, say, they're coming from aquaculture, so that's something else, not but bottom trawling. But this gives you a way, again, to take something that is like, very big. It's, the size of a continent and the whole industry and something. So, but then if you take it, you normalize it into a context, then you can understand the number more clearly. Okay, which is the essence of the talk. How do you make sense of big numbers? And with that, I'd like to send you with the last thing to think about. So any comments about that? Comments, thoughts?
I'm sorry, but I just don't understand how you can extrapolate that the data that we received was we know the total grams of all trawling and all fish picked up from trawling.
Yeah.
So you calculated that for 1 gram picked up from trawling, is 1 meter square of ocean. You can't say that if a fish weighs 10 grams, then it's if shrimp weighs 10 grams, it's 1 shrimp for 10 meters square.
Okay, so
You can't it's less.
okay, so there's 2 things here. One is, I'm not sure. So this is on average. On average, I think this is what it comes to. Like on average, every gram of this bottom trawl is associated with 1 meter squared.
That's okay.
Okay, so that's in terms of the average. Now you can talk about whether you could extrapolate from all the things to specifically shrimp. Okay, that's true. Here there's if I had more time, we could dwell more into this. And then what do you do when you have things that you need to, you have something more complicated, like you have a location, like a collection of things, and you want to focus on some specific sector within it. Okay, it's sometimes called as the problem of allocation. How do you allocate of the all, say, in terms, you have here an input, like say, like you spent area, and you get an output, say the weight. Okay, how do you allocate when it's only part? So then there's different ways to do it. You do the allocation, often you do it by mass, or you do it by money, or something like that. So now you could ask, okay, out of the mass of all the things that you get out of it, how much is shrimp? So it turns out it's, it's about, say 20% or something like that. Okay? And now you can say, okay, that's in terms of the weight. In terms of the area, how to explain it in the best way? Anyway, you can take that fraction and see, but also in terms of the area that that was ruined or that was affected, it's also you can't separate them. So you could just say, okay, on average, that's what I would get. Anyway, we could discuss it. Okay. So in the spirit maybe of taking these, big phenomena and trying to put it in a context one could follow and understand. Let's take the last, something that would be useful for the next meeting. And this is the following. Let's take another big phenomenon that is happening on Earth, and that's climate change. Okay? What does climate change do? It warms up the Earth. And let's say we wanted to adapt to it. Okay, there's mitigation, try to make it not work, and there's adaptation, trying to change things in order to be able to handle it. And we need both of them. But then there's this very naive way to adapt to it. Which is what? If I'm too hot, and I want to make things colder, I can decide to go up north. Or if I was in Australia, I would go down south. What? So right, you can basically, because it's colder in the poles and in the equator, one way of adaptation could be to just move. Let's say you're an animal or a plant or something like that. Okay. So now here's my question to you, or to your intuition. How fast do I need to move poleward to adapt to climate change? If you want, you can think about it as the velocity of climate change. What? Too cold?
Yeah.
Okay, sorry. Okay, so the question is clear? Okay, and in order to make it very concrete, let's say between, okay, so I could ask this way, but it's still a bit vague. I'm trying to take a more, as much as a concrete context that I would understand. So I would ask you between now and the next class, how far do you need to move? Okay? So just to make it interesting, let's give some options. Option A, let's see what's the best there. B, C. Let's say it's 100 micrometer, 100 millimeter, 100 meter. Just a second. Is the question clear? Okay, we're saying between now and the time we meet next week, same class, same subject, same everything. If you wanted to adapt to climate change, how much distance do you have to go towards the north? North is, anybody knows where north is? You're saying that way? My intuition is that way, actually. You say that, I say, okay. Okay. I think the train station is there. Okay. And then people say that way. Okay. Okay, we don't vote on where the train station is. That's not my role in life. But we do need to vote on whether it's, on your intuition. So you need to vote out either A, B, or C. Question is clear? You had something to say before?
Yeah, if you are taking into account seasonal effect or only... Average. Like, in the winter it's warmer than it used to be. In summer it's warmer. I think the seasons is a minor effect here. Okay. Who's voting for A? 100 microns? I would say half the class. Who's voting for B? 100 millimeters?
I don't know, a third of the class or another? Who's voting for 100 meter? 4 people. Okay. So the question is clear. Take care of yourself so you come back to class next week. You'll have another exercise waiting for you. Make sure to put it, bring us back to it with Moodle, not email. And if you have any questions, thoughts, something troubles you, be in touch with us. Bye-bye.